Any idea, Tegan? This one. Velocity time graph. Area under the velocity time graph. It starts off with 9. It ends off with 0. And the whole deceleration took 1.2 seconds based on what the question says. So we should be finding this area. So the distance moved. Half 9, 1.2. So I get 5.4 meters. Okay, so from here, the question asks for potential energy at B. So we do not have any pushing force, so we can't do work done along AB. So the only way is to do MGH by finding the distance here. Let's say this is your H. So we got to do gain in GPE. This is your MGH. The mass, we have it 0.5. The G is 10. The H is what we need to calculate. So Tiffany concept correct, but because of the wrong 5.4, then it's all wrong. We got to do Pythagoras theorem, right? So on 5.4 square, H square plus 3.9 square. Okay, so we're not going to do the math here. So the distance here is about then we sub in. Okay, this will give us gain in GPE 18.7 joules. So what we have over here, the 18.7, this is strictly what we call work done against gravity, okay, which is the gain in GPE. So this means that the amount of energy needed to raise the object by the height of 3.7 meters. Okay, we need a minimum amount of energy of 18.7 joules of energy. All right. So the next part here, we have loss in loss in kinetic energy. So essentially, the kinetic energy from a velocity of 9 to 0. So this is just a straight off half mv square, because all the energy here is lost. So we have half times mass is half times v square is 9 square. So we have about 20.3 joules. Now the numbers here don't match. By right, when it's moving up the slope, whatever loss in kinetic energy should equate to the loss in the should equate to the gain in gravitational potential. But by right, we only need to have 18.7 joules of energy to bring it all the way up to that certain height. But instead, we actually consume 20.3 joules to do only 18.7 joules of to do about 18.7 joules of work. So there is a loss over there. So where did the loss gone to? Most likely is the usual work done against friction. So suggest why it's not equal, right? So I would say that the loss in kinetic energy is equals to the sum of the gain in GPE and also work done against friction. So in this context, 20.3 and 18.7, that's a difference of 1.6. So the loss KE, gain in GPE, plus work done against friction, 20.3, 18.7, 1.6 joules. Okay, so this was used to lift it up. And this was needed because there is friction on the slope. Hence, we use more than the required energy. Okay, so I will just mention some of the energy was lost to overcome friction. Okay, yeah, please help me jot this down. Okay, my answer for this was it was more gradual, then it becomes very steep. Same thing, more gradual loss become very steep. Okay, so this is again, it's not a straight line due to the fact that Ke equals to half mv square. Okay, as you know, as the stone falls in, the velocity here, the v is actually larger. Okay, the v here will be smaller. So as a result, right, the Ke here, it scales off a lot more. Okay, we just take a simple 1 kg with a speed of 2, 1 kg with a speed of, let's say, 10 meters per second. The kinetic energy here based on half mv squared will be 4 joules. And then over here, the half mv squared will be 100 joules. So you can see that the scaling here is not linear. Okay, because for this is actually GPE. This is actually like free fall, right? So due to the Earth acceleration of g equals to 10 meters per second square, every 1 second the velocity increases by 10 meters. So if you look at the first second, 1 kg, 1 meter per second, this is time equals to 1, this is time equals to 2. So the increment here, this is actually 1 joule. But when it's like time equals to 10 seconds, the increment is so much larger already. So the higher your velocity, the more change into Ke will be. So that's why the last portion, the same amount of time, the drop in GPE is a lot more, the gain in Ke is a lot more. That's why it is the gradient looks like this. This is for GPE, this is for kinetic energy. Kinetic energy scales a lot more at the end. Megan, is this okay? Okay. Okay, the question here says that there's ball X is larger than ball Y. Ball Y is the one that's being hit. So the ask of velocity of Y will be greater, less, or equal to. So generally, it should be ball Y should have a larger. The basic concept here is due to conservation of energy. So ball Y should have a larger velocity. Okay, the working, I put it here. This is Ke of ball X, Ke of ball Y. Let's again use simple numbers. So let's say the mass of X is twice is twice of Y. So let's say X is 2 kg, Y is 1 kg. So if we do a half mv squared, half times 2, velocity of X squared equals to half times 1 velocity of y squared. So cancelling everything off, you can see that Vx squared is equals to half of Vy squared. So you bring it over, Vy squared is 2 times of Vx squared. So numerically, this will tell you that due to conservation of energy, the velocity of x is likely to be lesser. And the question says there's a smooth table, so there's likely that there's no friction. So we will assume, based on the smooth table, all the energy is transferred. Okay, so I'll say that in this case, the Ke of x will be transferred to form the Ke of y. Okay, something like that. The bottom part no need to show you the marker. It's just for our own understanding. Okay, if no question, okay, so for this case, the two areas are expressed in different units. So we got to do this sort of dimension. In the same case also for volume conversion. If we were to do a meter cube, it's the same thing. So we multiply by 1 meter 3 times. So we will multiply by 100 3 times. So the conversion will always be like this. Okay, that's all. So other than that, I think the first portion for the weight of the load is we are assuming that whatever that we can lift here. So the pressure across on both sides will be the same. So the question says the small piston has an area of 30 and it applies a force of 4. So pressure at the small piston, we will have a 4 over the area, which is 30. We need to divide by 10,000 to convert it to meter square. So force divided by area. Our force is 4. Our area is 30 over 10,000. Okay, this will be in Pascal. And then on pressure on the large side, so pressure of the small is equals to pressure of the large piston. So pressure of the small piston, okay, we have it here, 4 divided by 30 over 10,000 equals to, so for the pressure, it is the force, which is the weight, over the area, which is 0.15. Okay, this weight here is the force. So you bring it over, you should get a value of 200 newtons. Okay, this one, nothing much. So the large pistons, because we push it in, the water or the liquid will be pushed up. So we will say that the motion of the large piston is likely to move upwards. So large piston is going to move upwards, that's all. Okay, so in your answer in triple R, you mentioned that they cannot be compressed. You shouldn't use air because air can be compressed. So what's the effect of if air being able to compress? What's the significance to the whole setup? In fact, I'll just use what you have written. This is exactly what you write. So air can be compressed easily. So what is the impact of air being compressed easily? It will not be able to do something. Can you talk about the pressure at the small piston? And if you use air as the medium, what will happen to the pressure at the large piston? Yeah, you'll be small. Not say what is needed, but rather the pressure at the smaller piston will be larger, right? Then, because of the ability to compress, whatever pressure that is transmitted to the larger piston will be smaller. Make sense? Because the transmission will not be so good because of the compressibility. Okay. So you said because the air can be compressed easily, I'm going to use exactly what you have written here. Okay, and that the pressure exerted at the small piston, okay, cannot be transmitted to the other piston. By right, the next point that I'm going to give you, all right, it can be as a standalone answer for this question. But let's put this in to enhance everything. Okay, so if remember all these are all work done because you have done energy to um you have used energy to push the small piston. So this energy will be transmitted equally to the larger piston. So if the energy, right, wasn't transmitted over, the pressure wasn't transmitted over, even if it's transmitted, maybe there's a loss in the transmission, there's not so much of pressure transfer over, right? So that means whatever energy that you supply at a smaller end, okay, whatever pressure, whatever amount of energy that you push in over here, because we use gases, it's not transmitted to this side. So, Tegan, where do you think the energy has gone to? Because conservation of energy must have gone somewhere. So the energy that is used to push the small piston, where is it now? It must have gone somewhere, and hence the pressure is not transmitted. You agree we need energy to push the piston here, right? You will exert some sort of force, then that's energy to push it in. So eventually we say if we use air over here, the pressure is then not transmitted over. So this thing doesn't move, or even if it moves, it's a lot lesser than expected. So if that's the case, there must be some sort of the energy loss somewhere. So my question for you is, because we use air over here, right? It wasn't able to transmit over. So the energy initially that you pushed in, where is it now? The energy must have gone somewhere. So where's the energy gone to? Any idea? Tiffany, where do you think the energy gone to? Because whatever energy that we push in at the small piston must have went on to do some other stuff if it's not transmitted due to the air present. Tiffany, do you think yeah, it's something to do with the gas particles inside. Do you all think energy is needed to compress the air inside? Because if you push the piston in, there will be energy required to compress the air. So the compression of the air, right, causes the energy to be transmitted instead of to the larger piston. It is now used to compress the air. After compressing the air, the energy is gone already. So nothing gets transmitted over to the final side. So there's this this energy here, but the pressure cannot be transmitted over to the other side. And you can also add in the fact that that's due to, this is an official write-up for the compression. We call it due to work done against compressing the air. So this compression leads to a loss of energy. So there is no transmission to the larger piston side. That's why the larger pistons, either if there's still some energy left after the compression, it will lift up a lot lesser. But if there's no energy left after compressing the gas, then the piston doesn't even move at all. Okay, so this energy loss, we go and call it work done against compressing the air. That's why gases is horrible for this kind of hydraulic. Whereas in liquids, there is no compression, so the energy it's not wasted to compress the liquid, so it will be fully transmitted to the other side of the piston. Okay, that's the general idea. I need you all to, because the question says the barometer reading at the bottom. So that means at this point, the pressure is 76 cm of mercury. Over here is 70 cm of mercury. So the Tiffany, how come the higher you go, the lower the atmospheric pressure? Any idea, Tiffany? Okay. Yeah, because we are talking about H rho G over here, right? So since okay, you're talking about the numbers wise, but let's talk about this scenario. Just generally, why is it that the atmospheric pressure at the top of a high place is always less? You talk about measuring from the top, is somewhat correct. But so there's something that is a lot more at ground level compared to P that causes the pressure to be different. What is a lot more other than pressure, right? What causes the pressure to be a lot more at the base? Something must be a lot more that's present. So what is actually present in a larger quantity at the ground of the mountain compared to the top of the mountain? Something is a lot more at the base than at the top. What's that? Okay, it's called air. There's more air at the bottom than the air at the top, the column of air that we're talking about. So let's say there's this boundary here. That's where the air will exist. Okay, above this point here, it'll be like space, let's say. So the column of air above the 2 points, you will see that when you are high up at the mountain, the column of air above point P is only this column of air. So the amount of air particles that's pressing down on point A is only that much. But if you're at ground level, this is the column of air that's resting at a particular point. I mean, it doesn't look like that now, but it's just to visualize the concept of column of air above you. So at the bottom, there's definitely a longer column due to further away from the boundary. Okay, so one of the first things that I can do is I want to find out what's the difference in pressure between the bottom and point P. So the bottom pressure is larger, so our HOG at the bottom minus HOG at the top. Okay, the difference in pressure is 8,160 Pascal. So I can also say that based on this, right? The question wants to find out the height of the mountain. So at point P, so this is the height from ground level that we are interested in. So this height happened to be the height of the mountain. And same thing, there's a pressure difference here. The pressure difference will be 8160 Pascal with this particular height. So technically, I can do HOG. So the pressure difference is 8160. The height difference is the height of the mountain. Multiplied by the rho, I'm going to use the density of air because if you look at this as a barometer, this is like an air barometer, which gives you this height. This is the height that matters. And then from here, I get H equals to 663 meters. Because this is like the actual H here, okay, is due to the difference in pressure in this column of air, so to speak, instead of column of mercury. But we use the column of mercury to actually help us determine the value of 8160. So the height of the mountain, 663 meters, which equates to the difference in the column of air. Okay, so that's what we have. Point P and normal ground, right? What is going to happen to the boiling point of water when you move it up to a lower ground at point P, at the higher ground at point P? Will it be, with respect to 100 degrees Celsius at ground level, what would you think? The boiling will be higher, lower, or the same at point P. And a simple reason why. You can say. No clue. Okay, BP decrease is correct. So I mentioned that at point P, simple reason why. The pressure at the top is lower, right? At point P is lower, right? So if the pressure is lower, what can you say about the amount of force, right? The air particles is pressing on the surface of your liquid at point P at higher position. Do you think the force that is pushing on the surface of the liquid is higher or lower at point P? Yeah, so if it's the force acting on the surface is lower at a point P, do you think it's now easier for the liquid particles to push through since the force is bigger? Yeah. So as a result, the boiling point will be lower. So the main thing we want to see is the pressure at the top. Tiffany, make sense, the concept? Right at the top, lower pressure. Lower pressure means the force resting on the surface is less. And if the force resting on the surface is less at point P, it is easier for the particles to push through and turn into a gas. That's why the boiling temperature will be a lot lesser because now they don't need so much energy to push through. So it will start to boil at lower than 100. Kind of make sense? Yeah. Let us put this into words. Sea level means flat on the ground. Okay, something like this. So after we mentioned that temperature rise, pressure rise, the flask actually expands and the volume increase. So now with the concept is due to that because of the larger volume. With larger volume of the flask, okay, this will actually cause the pressure to fall. Okay, due to the larger volume, then the frequency of collision decrease and all those stuff. Okay, so this when it starts to expand, it will keep falling. It will fall until the point where the pressure inside the flask is equal to pressure outside the flask. Okay, so pressure inside the same as pressure outside, then the expansion will stop. The pressure will also stop changing. Again, I'll leave the two numbers here. You see if we can calculate it. That should be quite okay. I think these are the numbers. This is your time axis. This should be your period, 0.2 seconds. It is the main thing that I need to show. Okay, if all right, let's take a look at 7. So so for this question, you're going to let it cut through multiple times. So this simply means that the light ray, when it goes into the diamond, it will be trapped inside and keeps reflecting off the surface without coming off. So if the light ray is trapped within the diamond and doesn't come out, then it looks like it is sparkling. Okay, so the concept behind this is allowing the light ray to cut it in such a way that most of the time the light, when it reflects, it will always be greater than critical angle, so it doesn't allow the lights to come off. So it looks like there's multiple reflection, which essentially is just experiencing multiple total internal reflection. So in the diamond, it also normally what we call in the denser medium, because TRR only occurs in the denser medium. So in this case, in the diamond also means in the denser medium. Okay, please help me jot this down. Okay, if no questions for this part, you can help me do up these two also. Critical angle is, my answer is 24.6. And the angle of incidence is about 15.5. Okay, let's do the part 2. So calculate the angle of incidence for it to emit from the light. So can I say that over here, this is 40, right? So the angle that you will go off is likely to be going off with an angle of refraction of 40. So this is the I that you want. That's it. Oh, so this is the angle of incidence. And then the refracted ray that comes off is coming out at 40. So for B part 2, will be N equals to sine R over sine I. And then the refractive index, I think, is 2.4, right? 2.4. So I'll have sine 40 over sine I. Why is it sine 40? Because the light ray, in this case, shows that it comes out. You see the arrowhead? It comes out at an angle of 40. So the R is 40. So now we just want to find out what's the I. That's it. Right, it's always big angle over small angle, R over median. Okay, that's all for this part here. Yeah, Tiffany, correct already. Okay, let's talk about induction. So two things that we need to include in our answers for induction. Number one is particle movement. Number two is there's no contact between the conductors and the charging body. So in this case, this is what I would say. Okay, the charging body is also known as the charged particle that will cause the particles to move in a certain way. So something like our usual positive charge sphere or negative charge sphere or positive rod, that kind of thing. Okay, so this is the normal induction process. So first off, okay, we're going to place X near to Y. And then literally connect the Earth to Y. Then disconnect the Earth to plate Y. And number 4, remove the X from Y. Because the question wants us to describe the steps. Even if you look at your answer, what's the difference from yours and mine? Okay, but anyway, even if the question doesn't need it, but let's also go through the explaining the science behind how this is done. So when we place it close, okay, step 1 in red, you will cause the charges to separate. Okay, this is due to step 1. Number 2, if you connect the earth wire, then these electrons will run away. Step number 3, due to the electrons running away, now there's excess positive to negative charges. So after you remove this away, the rod becomes something like this. And hence, the last part in yellow, we will literally remove this away. And then what's left behind is the positive charges that's in excess of the negative. Hence, it becomes a positive rod. Okay, so why do we need wooden stand? Because the rods, just now is a positive rod, right? So if you don't have a wooden stand, the electrons will run up to neutralize it. So we do not want any charges to flow in and out of it. It needs to be wooden. It will mention that wood is a poor conductor of electricity and will not allow charges to flow in and out. In and out of the conductor. That's all. I'll leave the numbers here and then help me work this out. If I cannot get it next lesson, we will go through this. So I'll give you the numbers. Dagan, you jot it down. Okay. All right. If no questions for this, okay. Tiffany, those written parts, I'll mark for you. Again, I totally forgotten to go back to mark this. So I'll mark for you. Then we'll go through those written stuff the next lesson on Monday. So let's go on to see some calculation question. Okay, let's look at 11, question 11C. Tiffany, this question, this part you need to take a look again. Again, I give you the values. This is 47.0 kilojoule. This is 0.0189 kg. Okay, can you read the question first again, and then yeah, try out these two. Okay, eventually they reach a temperature of 55. So this total value, right? To reach the milk for the milk to reach 20 to 55, you need 47,000 joules. So that means in this case, right, our heat loss by the steam. Okay, steam starts off with 120 degrees Celsius steam. Eventually, it needs to reach liquid state at 55 degrees C. Do you agree? Because in your answer, you only show ml only. It's not correct. How do you move from 120 degrees Celsius steam to eventually their final mixture of liquids? How many steps are there in between? Okay, so how would you describe the next box? You will go from 120 degrees Celsius steam to, yeah, 100 degrees Celsius steam, which is in this case a MC theta for the steam. Okay, if you have another two more stages, then what do you describe the next box? Hundred degrees Celsius liquid state, right? Correct. 100 degrees Celsius liquid state. This is your MLV, and finally it goes here, which is the MC theta. So this is the heat loss by the steam. Okay, you try and see if you can get this number now. So generally, in this case, the heat loss by steam will be equals to this value. It will be equals to this value, which is the heat gain by the cup and the milk itself. So this will be equivalent to 47,000. So let's talk about the M. The M is what we want to find. We don't have it. So this is the first portion is MC theta for the steam. So M times the C of steam. Do we have the C of steam? Specific capacity, this is the one. And then for steam is 2010. So for the first part here in blue, this is 2010 multiplied by 20 degree. Okay, let's talk about the ml. So plus in this case, the mass times the addition to this. This is your latent heat of vaporization. So latent heat of vaporization is this value, water. This is for solid, so this is not the case. We are using this 2.26 times 10 to the power of 6. Okay, and the last one is the MC theta for the water stage. So again, we have M. C of water should be 4002. The difference in temperature is 45 from 100 drops down to 55. Okay, this is equals to heat gain by the milk and the container. So that is 47,000. Okay, I put it as 47,000, ignoring all those behind. Then solve for M, it should be in the region of 0.0189 kg. Tiffany got it?